colleagues. I'm glad to see all of you. Thank you for your thanks for your interest in our workshop, and I'm very glad to see all of you with health and you in person. So this year we have 4 presentations on 2 sessions. Each presentation should be presented by 30 minutes, 20 minutes for the presentation and 10 minutes for the questions. So on first session, our first presentation is Alexander Vitichevsky, Vladimir Pichanenko, and Vladislav Volk, Algebraic Virtual Machine Project. Please, Alexander.
Okay. Should I go to computer, yeah?
Maybe yes. One second, please. Presentation.
Yes.
Okay. Okay. So.
Okay. So my presentation is titled Algebraic Virtual Machine Project, and we present the participant of this project from 3 enterprises, from 3 organizations. It's a private enterprise, Litsoft, Institute of Cybernetics, Rushkov Institute of Cybernetics of National Academy of Science, National Academy of Science, and Kherson University. So first of all, I would like to present our team and what is the project, where it's come from, and so it's we are the follower of the great algebraic school, which was founded by Viktor Grushkov. He is founder of Institute of Cybernetics, and his follower, Vitichevsky senior academician, author of the computer algebra theories, methods, creator of the algebraic programming insertion modeling system. And so we are the follower. It's a lot of followers in different countries.
I'm sorry.
Followers in the different countries. And our methods, formal methods, our main goal is to deploy formal methods in different industrial subject domain. Next, please. And let me refer the history of the algebraic school. So we have in the 1780s years of the previous century the automated theorem proving machine, the first prover, one of the first prover in the world. We have also, we were creators of the first parallel operation system with distributed memory. From the 90s we started the work of the creation of the algebraic programming system. The task was to provide the resolving of different tasks on different theories, and by algebraic methods. In beginning of this century, the insertion modeling system and the generalization of algebraic theory has been created.
I'm sorry.
That's wrong.
Okay.
And this we work with we start work with Motorola. We have cooperation with Motorola maybe 10 years, more than 10 years, and we deploy our formal methods and the very interesting technology of the symbolic modeling, of the algebraic magic, and other formal methods were invented. In the last 10 years we work in the application in different subject domain, and some use case I will show you today. And in the in the previous year, 2020, the algebraic virtual machine has been invented, which is involved all these methods into one algebraic server where the user can use any formal methods for resolving of his algebraic task. Next, please. So the main goal of the AVM is to deploy the algebraic approach in the software and hardware development process. It's also one of the tasks is to provide compliance with the modern standards of the medicine, automotive system, in space and avionic, and we collaborate with this. Что
Sorry.
бывает так?
Да не, я просто проверяю, чтобы люди заходили.
Да.
Время от времени надо смотреть.
Ясно.
Continue, please.
Okay, thank you. So, and the theory of agent environment has been deployed in this system, and also the different methods like symbolic modeling, automated proving, and the a lot of and we also use it for the research in the natural subject domains like chemistry, biology, and economy. Next, please. So a little background of the algebraic knowledge. This is behavioral algebra. Behavioral algebra was developed by British scientists David Gilbert and Letichevsky Senior in 1997. This is the two sorts algebra over actions and behaviors. There are two entities, and we have operations over behavior. These are the prefixing and alternative and non-deterministic choice, also parallel and sequential composition. And this operation allow to present the different control flow of the process in different subject domain. Also, I would like to say that we have the mapping to the graphical presentation. It's a UCM use case maps, and different graphical construct corresponds to algebraic specification. So here the example of the behavior, and so the next please slide. The actions are presented in algebraic action, presented as precondition and postcondition. And precondition is some expression in some formal theory like a Boolean integer or real theory or symbolic theory. It can be also presented in MSC message sequence chart diagram. Message sequence chart diagram, and illustrate these actions by some graphical elements like ascending of message. Next, please. Here are the example of presentation of C program as in behavioral algebra. So you can see the equations. It's equations in behavioral algebra. The mapping to the graphical, and you can see the nothing to see on the screen, okay. And also the actions, they are given as MSC diagram. Next, please. The other example, how to present the low-level code in algebra behavior. So we have the set of the machine instruction of Intel x80.
Sorry.
x86 Intel instruction, and here you can see press twice the space bar, with два раза space bar нажмите. Okay. And here are the behavior expressions and behavior actions. Next, please. The other example is VHDL specification. So on the left we have the hardware design language, and this language is the formal language, and in the right side you can see the presentation of this language also in algebraic equation. Next please. Also we have the specification of FPGA circuits and also by means of the algebra behavior and algebra actions. The next please. So why we presented this all specification from different subject domain in behavior? Because last 20 years it was developed a lot of formal methods in the scope of the behavior algebra. So when we translate the some specification, programming language or hardware specification, or we can create some model, so then we are in the world of the behavior algebra, and we can apply a plethora of formal methods. This is the short list, not full list. So one of the main is the symbolic execution forward and backward. Symbolic execution was invented in the beginning of the century. We were one of the first in the world who used the symbolic execution in industrial for Motorola. Also static proving, it's automatic proving of theorem. So we can prove some statement in the scope of behavior algebra. As invariant generation, algebraic matching, approximation for the nonlinear equations, and methods of abstract interpretation. So the property which we can do is we can prove the property. For example, we have a model, we can prove the absence of non-determinism, the absence of deadlock, timing property, signal races in the hardware, starvations, and other safety and liveness properties. The next one. So this is the full scheme, scheme or high-level design of the algebraic virtual machine. So we have the lot of languages, programming languages or specification in the front end. We have front end and back end server. Front end, it's a web application, and it convert the some specification, convert this input specification to behavior algebra expression, but also we can develop the model in the term of behavior algebra specification. It is important for research in different nature, in different subject domains. So on this server we have a lot of algebraic assets. So these are the different theories presented, axioms, theorem, definition for different theories. We have the automatic solvers in the scope of these theories, Pressburger solver, Fourier-Motzkin, byte solver. These are the solving program solvers that were developed by our team. Also we have the third-party solvers. These are the that's Microsoft and CVC4, Stanford University, etc. Formal method that I listed before, and we have the database of pattern for different subject domain, models of different vulnerability, or etc. Also, anyone can, if you work in the scope of the behavioral algebra, you can add your own formal methods, and also we will, now it's under development, we will provide the machine learning of efficiency of model of classification, what kind of methods you will use for resolving of different tasks. This is just in the initial stage, and this is one of the future. The next, please. So now some use case. The first use case is model-driven development. So you know what is model-driven development in the so we have some development process continue. We can define for example 3 main stages requiring gathering, designing, coding stage and testing stage, and we use different formal methods on every stage. For example, we can verify the requirement, provide the verification if requirements are given in the formal way, because we have can provide the manual, as it was experienced with Motorola. We provide the manual formalization required and created in behavioral algebra. But also we would like to do the algebraic automatic translation of the formal language of the requirement specification, BPMN, CSML, etc. So design and coding stay the same, verification of design and generation of test on different stages for testing stage. Next, please. So also in model driven, we have on every stage we have a model in the behavioral algebra, and we can provide the verification of this model on the different stage. If design use the traditional design language, UML, UCM, we can translate it to behavioral algebra and provide verification in the term of behavioral algebra. Next, please. Also, it is model driven. It anticipates the code generation on every stage, because if you have the formal, you can create the code in the term of design language and then detailize it. You can create some carcass, some frame of design or some frame of code, and then detailize it in the term of code and provide the test on every stage. The next one. These are what is formal verification in every stage. These are methods that I mentioned before. The next, please. Next. Model-based testing is the technology which use the generation from behavioral algebra, немножко дольше, чуть бы все равно. Behavioral algebra specification. We have the white box testing when we use this is our invention, white box testing, when together with Motorola we have the parallel execution of the source code of the some system and execution, symbolic execution of the execution model of system, and we compare the environment for for equivalence. So these techniques can be used in regression testing and integration testing, because it's just use the model-based testing only for those parts that are affected for integration or for regression. The next one. Cybersecurity is the the most interesting subject domain, and it was interesting after when the DARPA launched Cybercrime Challenge to create defensive systems, and the 3 first medalists, Mayhem, Sandra, and Mechanical Fish, all are from the United States. They use the symbolic modeling for the vulnerability detection and for the detection of the cyber attacks. The next, please. So we use the notions of the patterns of the vulnerability, and it can be also presented as the model in behavior algebra. So this is the example of vulnerability. It's cover a lot of cases, stack-based buffer or overflow. Next, please. Also, we can present in the behavior algebra the attacks. For example, there are two known attacks, meltdown and spectre. Also can be presented this one of the in the C intruders code in C language in machine instruction, and this is in behavior algebra. Next one. This is the deploying and application of technology. So we have binary code, unknown binary code or binary code that was compiled and selected. We provided disassembly conversion into the algebraic model, and then we provide the methods of the algebraic matching. We match the code in the term of behavioral algebra with the patterns, with algebraic patterns of vulnerability. And then we can we detect vulnerability, and then we can create an exploit that can use in testing. Next, please. The other one, it's detection of the intruders or the virus or the Trojan in the loaded process. So we can scan the new and find the suspicious non-registered or some process. Then also we can disassemble it, convert to algebra, and to provide the algebraic matching with the set of models of different intruders. So in the cybersecurity, in virusology, we have the notions of the signature, virus signature. So we have the algebraic virus signature. So this is the technology when we can, when the AVM work as a virus detection. The next, please. This is the combination of algebraic approach and machine learning. So, of course, the algebraic operations and with usage solver is too expensive, and it's efficient for static detection. In dynamics, it should be performed quickly. So then it may be time consuming, and we can miss the attacks. For this purpose, we use the combination with the usage of the classification model, which was trained on some data sets for different attacks. And when we have the suspicion, the suspicious process, the suspicious attack, it can be detected first by classification model quickly, and then it activates algebraic matching. Why we do these two? Because algebraic matching is too precise procedure, and we can avoid the false positive cases. The next please. The other one is the fuzzing techniques, the testing for vulnerability detection. These methods was the more efficient for detection of zero-day vulnerability, and it also use the if we have some binary code to test, we can what is the fuzz test? It's fuzzing testing when we provide the input of the critical of unexpected input values. But in the fuzzers, it's a program which use fuzzing techniques for vulnerability detection, and sometimes it use randomly, it create randomly this critical, but some fuzzers use the monitor the coverage of the control flow. In our case, we use some prompts. We find some prompts for possible vulnerability, and for this we use the translation to behavior algebra. We use lightweight symbolic modeling. It's also the quick symbolic modeling, also our invention. and then we find the prompt, the place for possible vulnerability, and we generate the test, and we execute the test and obtain the test verdicts with it good or not. So next one. So thank you for attention. This is the very short, brief survey of the AVM project. So next I would like to show you the demo. The demo of the AVM project is from cybersecurity domain, and this is the user interface that we can see from the website. So we can upload some, for example, we can upload some project, vulnerability detection, we upload the machine instruction, and then we convert it to algebraic model. You can see this is the algebraic model. So these are the instructions, and now it will demonstrate how it converts to model. Model convert to the description of the environment, algebraic environment. Also these are actions, and also we can see behavior. So many behavior shall be the behavior shall be. Then we can run full algebraic matching, and we can define the we have database pattern of blockchain. We can use for blockchain attacks, and we can use the pattern for Intel 86 vulnerability. We select buffer overflow, stack damage vulnerability, and let's try to find this vulnerability in the binary code. So we launch the and then it will finish 1, 2, 3, 4, and it will finished, and it's successfully finished, and it created the trace. It created the trace, one of the trace that leads to vulnerability. And now we can use our visualization tool for algebraic virtual machine, visual code. We have different visualization tools. We have visual code, and we can highlight the place of vulnerability. This is by the red color, and then the yellow color is the path, it's exploit, which is the path behavior scenario of the program, which is lead to vulnerability. So it's all. Thank you for attention. Questions? Here the authors of the front end.
I don't know, do you use some new language here, or it's a plan or some old language that we know?
It's old language, it's a plan, but it's a plan, the generic language. We applied the language of the rewriting rules, and it's an algebraic generic language, and we just organize it as the set of actions and set of behaviors. But it's the same language which we used in the algebraic system in the 90s. So nothing new, it's a terms, language of terms, algebraic terms.
Okay, and when we can learn this, a plan and this machine, some writings about it, some textbook? Do we have something about it?
Well, maybe you can say like co-author. We can. Where? When or where?
We have separate site.
We have
website
site with tutorial,
with
articles.
Tutorial site,
Yes, with tutorial, and with the possibility to do exercises. This is maintained in this university by your department.
But we don't have textbook, yes?
Those books is very short, was in 90s. I remember the APS, how to
We have few user manuals
yeah, and
for APS, but of course we doesn't have for now a textbook, but
For,
we will
yeah.
try to create it
yes, it's
in
our
the
task.
nearest future.
It's our task to create the for the good description of AVM and the core languages that we can use for these purposes. Okay.
I have a question.
Okay. Yes.
In your presentation, you said that you have implemented some kind of lightweight symbolic modeling.
Some words about
What? does
what
it-
is okay. Lightweight. Okay. So this is lightweight. We just following. We used. If we provide the symbolic modeling, the complete symbolic modeling, we use the already environment, and we use to transform it by predicate transformer. And now the very light. It's we use the we should monitor where is the dirty memory. Just monitor. Now it is in register. Now it is in some place of memory. The very light, because we assume that all memory always will be dirty. The where, but you should watch. Does it will it trap to the stack or no? So it just to watch, or it is in register, or it is in the memory. It is in register again. It is in the memory. So without computation, the other lightweight, it's just concolic, not concolic, just concrete computation of possible address, because you use the virtual address, and when you write the memory, we define the strict address. But we of course we assume that they will not intersect these two memories. And for this purpose, we just compute the value of address. But we prepare the paper now, and I can send you. You can see how it is implemented. Just computing of address, concrete computer, and it is just monitoring where is the dirty memories. Dirty memories are the memories which come from outside, the possible attack. Okay.
Thanks. That's the question.
No,
Oh.
we haven't.
Thank you, Alexander, for the presentation.
Thanks for you, for others.
I think all other questions will be after. Awesome.
So our next presentation is Alexander Weidlit, quantization of neural networks.
Yes. I better sit near the computer.
Okay. Is it your presentation? Yeah.
Yeah.
Okay.
Okay. Thank you. I will say. I will sit here. If you don't against. Yes. So this presentation is introduction to dynamic quantum models. Dynamic quantum models is topic that I developed some recent years. And I start with motivations. There are many motivations for this topic. First motivation, the structural stability of mathematical models is the qualitative invariance under small perturbations of this model, is necessary condition for its correctness. and it is also necessary for application of computational methods. For example, we solve some optimization problem. This is some local maximums, and if arbitrarily small perturbation can change all picture of these extremes, of course we can fit absolutely another solving. So we can't solve in these obstacles, and so this problem is very good known for machine learning. After Smale's works, it became clear that dynamics of the system of general form is not structurally stable. It's works of 60s, 70s years. Therefore, for now, there is no strict mathematical basis for modeling and computational analysis. The real situation is that. So the contradiction appears in science. According to physicists, dynamics is simple and universal. Another motivation, paradox in cognition. The classical systems of artificial intelligence are naturally and inevitably associated with classical logic and discrete mathematics. It's very well known. However, mathematical models of neural network are usually continuous and stochastic, naturally associated with fuzzy logic. So, the representations and models of knowledge that unchanged and undeniable, at least since Aristotle, apparently clearly do not correspond to the cognitive models that are obtained as a result of studying the human brain. Because neuron networks, it's model of human brain. It's very well known fact. And there is third motivation that I say orally, really historically first. Vision of physicists of quantum mechanics is absolutely different from formal apparatus of quantum mechanics. And this is some problem. This is some problem that I think, I believe, solved by this theory. So, dynamic quantum model. The idea of dynamic quantum model is very natural and very easy, even obviously. Practically, I involve fluctuations because we can't exclude fluctuations really, and we can say that quantum mechanics show it. So, I believe this is the solution of all these problems. What is DQM? DQM is a perturbation of smooth dynamical system only by a Markov cascade given by some transition function, and so we can by this learn the dynamic of this dynamic quantum model by this transition function. DQM, discretization and representation. DQM is defined at first. DQM is defined for any dynamical system given on any smooth Riemannian manifold. As a Markov cascade, any DQM is approximated by a Markov chain and a compact set by a funny Markov chain arbitrarily exactly on infinity time. Thus we can think of DQM simply as a Markov chain. If we build an approximate model of a given theorem of software application using neural network training, then we will get exactly the DQM of this object. So, neural network is an example of DQM, and moreover, this is the general example. Really, the only generalization that in neural network define domain is simplex, and here we can and there we can consider arbitrary domain. DQM is so named because for Hamiltonian systems it is simply related to the corresponding quantum systems. That is corresponding Schrödinger equation. It was the first step, it was the first aim of building DQM, and DQM construction is only method for solving spectral problems. And here is some example of this. It's very difficult very difficult topic of solving spectral problems in quantum mechanics, and here it's much easier. Here is much easier, and here is examples of some problems that wasn't solved by traditional methods. Thus, we believe that DQM is a bridge between the formal calculus of quantum mechanics and the intuitive vision of physicists. So now we will move to answers to our contradictions. First, DQM structural stability. It turns out that just taking into account random fluctuations necessary for transition to the quantum model of reality allows us to return in fact to the simple picture of Poincaré dynamics. It's first idea here by Poincaré that then the picture become much more and more difficult, and because of this we can turn to this first picture. We have a dense set of structurally stable systems. The structurally stable realizations of DQM are everywhere dense and open. We can prove it on the set of all DQM realizations. So we believe this is the full answer to the contradiction in dynamics. And here is the application of such approach to traditional smooth dynamics. When fluctuations tend to zero, i.e. in the semi-classical limit value, DQM goes into initial smooth dynamics. In this way, we the old problem of equivalence of structural stability and hyperbolicity for smooth discrete dynamical system was established. The real proposition 2 is answer for this first question. It's absolutely absolutely answer for this question. That is, if two diffeomorphisms are arbitrarily close, then such diffeomorphism is uniformly hyperbolic. Absolutely. The converse proposition, the converse settlement, well known. Now the answer to contradiction 2. The contradiction in cognitive systems. So let G be a given smooth function on phase space equal to 1 on the trajectory of the original smooth system and 0 outside some neighborhood of it. We can interpret it as the function of thrust. So in this paper, DQM is defined and constructed universally for Hamilton systems and thus systems. What is DQM spectrum in general form? Physically, eigenvalue, the point in the spectrum, is the value of Hamiltonian H energy obtained as a result of the most accurate experiments. What is spectrum in this situation? Similarly, in this situation, eigenvalue, that is the point of the QM spectrum, is interpreted exactly as the average value of thrust of logical conclusions in all these trees. Average in all these trees. We believe that the following statement realizes the Niels Bohr's idea of quantizing cognitive systems. We consider the two-dimensional dynamical system, the compact phase space of which is filled with closed phase scales. Then we can generalize well-known Bohr-Sommerfeld condition from Hamilton systems to this situation. And I hope this is answer for ideas of Niels Bohr. And now we will move to DQM algorithms. The structural stability of the general form DQM opens the way to a mathematically grounded numerical analysis of dynamics. This allows to clearly understand the DQM dynamics and build effective algorithms. And they one additional mention: these algorithms are always oriented toward parallel computing. The first example was the Hannon system. It's a well-known system, and it was well known that this system is hyperbolic. But this method gives us possibility to prove it rigorously, including using computer, of course, using computer calculations, but this is rigorous proof. DQM in optimization problems and neural networks. One of very known problems I recently said about it in neural networks and in other problems is local extremes. So we propose some algorithm that can find the global extreme, and this algorithm is rather rapid for at least for small dimensions, and at finish I announce a new algorithm with which I deal just now. It's a training algorithm for neural networks. As we know, the traditional algorithm backpropagation is algorithm of first order of convergence. First order. And this algorithm, second order of convergence, is a Newton method. Also, it has no drawbacks of the traditional backpropagation method. That is, the learning rate calculated automatically in each moment of calculations. The ravens are bypassed, and we can use parallel computing essentially in this algorithm, because backpropagation can't use parallel computing. Thank you for your attention.
Questions?
Well, this is the new methods of neural network creation, yes? Or
As for Finnish algorithm, first, that is, I have first programs, but these programs is very far from perfect. Its algorithm is now ready, but I in study of study possibilities to implementation in.
So the difference is the good parallelism, yes, in all this algorithm. The difference from the back propagation, yeah.
No, there are. Please.
I said that this
Last.
is the
Last.
yes.
No. Control end. Where is end? Control end.
This is the last one.
Uh-huh. There are some, I even can say many news. At first, it's algorithm of second order of convergence.
Second one, yes, I understood.
It's much more rapid, much more rapid.
More efficient.
No, where is it? Where is it? Where is my? Thank you. The second, there are many problems with learning rate, because learning rate we
calculated automatically.
we define arbitrarily.
Yes.
We don't know about it, and in this algorithm we calculate it each moment. That is really we know in what moment we this algorithm know in what moment we must change learning rate, and then it's changed. And this algorithm, we can bypass trends. Yes, because it's very serious problem for neural networks. Yes, and we bypass it by using parallel computing.
Aha, you bypass it.
We bypass it by using parallel.
Okay.